ونمشي نعلمهم ونقول لهم ما يطلع عندي حد.
We are live.
السلام عليكم. I think it's time to start. Can I have a private message باللي everything is going good و the sound is well heard وكل شيء كيتسمع مزيان. All right, thank you guys. Let's start. The event ديال اليوم is basically something اللي الأغلبية ديال الناس اللي كانوا في TensorFlow user group are asking اللي هو we want to talk about TensorFlow, we want to introduce how TensorFlow works ونهضروا على دوك لي ديتاي ديالو كاملين en général. Donc باش ما نطولش about me, my name is Abdurrahman Jaiz. I am a TF UJ organizer ديال Casablanca. I'm a data scientist. I do machine learning, deep learning, NLP, Python. I use computer vision, and also I'm in my third year for PhD. So, بلا ما نعطلكم, let's start the talk and let's hope we have a good beginning. So, what is TensorFlow? TensorFlow is an open source library developed by Google Brain team for high performance numerical computations. It can be used in many use cases involving machine learning or deep learning. One may argue that using TensorFlow to machine learning is a bit of resource wastage, ولكن for deep learning, it is one of the best tools out there. So TensorFlow makes the deep learning easier for accessible developers and researchers by omitting headache need to develop things from the ground level. Uh, Honestly, it is actually the purpose of any library to make things easy للناس. ولكن of course there are alternatives competitors for TensorFlow كاين PyTorch, MXNet, Theano, Chainer, etc. But with regards to forums or resources and number of users اللي كاينين, TensorFlow is still the leading in number one في هذه القضية. So basically TensorFlow is an open source deep learning library اللي فيها أكثر من 1800 contributor worldwide using Apache 2.0 license و easy to learn and use for beginners and experts and available for everyone. So the best way to do this وتجربوه is to go in Colab and test it. You need to touch your ما محتاجينش تديروا شي touching في local systems ديالكم. The best thing you can do is you can go today, install it في Colab, just use pipe, install TensorFlow and it will work with no problems. So why TensorFlow؟ علاش كنخدموا به؟ أول حاجة open source. It supports both CPU and GPU computations. It has faster compilations compared to other libraries in the matter of time. Also, his API or its API is available in Python, C++, JavaScript, Java, Go, and Swift. However, languages other than Python are not yet covered by the API stability promises, but they having a good vision, good futures ahead. So I guess it is enough with background stories. We will move on to the main concept of TensorFlow, اللي هما tensors and graphs. Okay, tensors. TensorFlow has a different programming paradigm than other similar libraries. The main concept behind it is called as a graph. So in general, TensorFlow is a framework composed of two core building blocks: a library for defining computational graphs and a runtime for executing such graphs on a variety of different hardware. So first we build, or rather write the graph, and then we execute هذاك the graph. So what is the graph exactly? Well, it is actually simple. A graph is a collection of multiple operations. We call them nodes. Operations can be taking inputs, processing or performing some calculations, and maybe giving output. Most of the time they are giving outputs, etc. With just words, it will be hard to understand. So let me explain it with an example. So consider a function f, the function you're seeing right now. If I show it with a visual TensorFlow graph, it will be like the image you are seeing now. Each circle in this graph is an operation node. So, okay, here is an example of a very simple program. To create a computational graph out of this program, we create nodes for each of the operations in our program, along with the input variables A and B. In fact, A and B could be constant if they don't change. If one node is used as the input to another operation, we draw a direct arrow that goes from one node to another. The computational graph for this program might look like something like this. So this graph is drawn from left to right. But you may also find graphs that are drawn from top to bottom, or vice versa. The reason why I chose the former is simply because I find it more readable. The computational graph above also represents distinct computational steps that we need to execute to arrive to our final outcome. First, we create two constant A and B, then we multiply them, take their sum, and use the result of those two operations to divide one by the other. And finally, we print out the result. Sarah, this is not difficult. This is not too difficult. But the question is, why do we need a computational graph for this? What are the advantages of organizing computations as the direct graph? First of all, a computational graph is a more abstract way of describing a computer program and its computations. At the most fundamental level, uh, most computer programmers are mainly composed of um, two things. We have primitive operations and an order in which these operations are executed, often sequentially, ولكن they are working as line by line. This means we would first multiply A and B, and only when this expression was evaluated, we would take their sum. So the program specifies the order of execution, but computational graphs exclusively specify dependencies across hierarchical operations. In other words, how would the input out of these operations flow from one operations to another? This allows parallelism or dependencies, driving headache scheduling ليكيكون. If we look at our computational graph, we see that we could execute the multiplication and the addition in parallel. That's because these two operations do not depend on each other. So we can use the topology of the graph to drive the scheduling of the operations and execute them in the most efficient manner. Example, maybe we are using multiple GPUs on a single machine, or even distribute the execution across multiple machines when using a complex program. So TensorFlow does exactly this. It can assign the operations that do not depend on each other to different cores with minimal input from the person who actually writes the program, just by constructing a directed graph that's can run everywhere. So that's awesome, don't you think? It I think now you got my point. Let's move on coding so that I can expose you to the concept of building the graph, running the graph, and how we work with variable types. So let's have a code walkthrough and discuss the mentioned stuff. As you can see, we first have to import the TensorFlow. GF is a sort of industry standard. However, there is no hard fast rule that you need to stick to that. In the next step, I have taken three inputs. As you can see, those three inputs are in different variable types. There is placeholders, variables, and constant. Placeholders is a variable that is not assigned in the graph build stage. It acts as a placeholder, so that's where the name placeholders came from originally, which is reserved to capture inputs usually from a data set, random number generation, or user input. When initializing, we have to specify the data type of the placeholder, and there are two more optional features that can be specified: name and shape. Shape is actually the dimensions that we know. And by the way, notice the syntax of the placeholder coming with a simple p. Okay, one more time. A placeholder allows us to feed data into the graph from outside, and unlike variables, they don't need to be initialized. Placeholders simply define the shape and the data type, and we can think of placeholders as empty nodes in the graph where the value is provided later on. They are typically used for feeding in inputs and labels. So variables is changeable value, which is assigned within the graph building stage or creation stage, either directly or a result of a calculation. So it's a similar to the concept of variable in any programming language. Mentioning the data type is actually optional. Notice the capital V in the syntax. Think of TensorFlow variable like normal variables in our computer programs. A variable can be modified at any point in time, but the difference is that they have to be initialized before running the graph in a session. They represent changeable parameters within a hierarchical graph. A good example for variable would be the weight Euler bias in a neural network. Also constant. They are a fixed value which is assigned within the graph build stage. It's similar to the concept of constant in any programming language also. And in here, also mentioning the data type is optional when working with constants. Okay, since now you know the type of variables, let's move on with the code. and see in the next line, you can see the calculations. Mind that I did these steps one by one in the visual graph, but here I wrote it in one line. Both ways are correct. So in the code, F denotes the final step of the operations, which means it is the final step in the graph. Operations represents node in the graph that perform computations on tensors. So now at this point we are done with creating the graph. Next we need to run it, and for that we need TensorFlow session. It encapsulates the operations, uh, which mean the graph in general. So the operations environment is the graph. We initialize the session object as a ses. Ses is just also the industry standard name. You can change it if you want. And also a session creates a runtime in which operations are executed and tensors are evaluated. It also allocates memory and holds the value of intermediate results and variables. And in the next two lines, we run this session. First, to initialize all variables, then go to run the graph. Note that to run the graph, we need to run the final step of the graph. In our case, it's F. So since we used a placeholder, we should feed a value to it before running the graph. A graph is like a central hub that connects all the variables, placeholder, constants to the operations. So again, since we used a placeholder, we need to feed it some data as highlighted in the code. If A is a variable or maybe a constant, instead of being a placeholder, you can just run the graph with session.run and you can give it F as a parameter. So remember from the beginning that we said TensorFlow is composed of two parts: a library for defining computational graphs and a runtime for executing these graphs. That's the graph and the session. The graph class is used to construct the computational graph, and the session is used to execute and evaluate all other subset of nodes. The main advantage of deferred execution is that during the definition of the computational graph, we can construct very complex expressions without directly evaluating them and allocating the space in memory that is needed. For example, if we use NumPy to define a large matrix, say a trillion by a trillion, we would immediately get out a memory error. In TensorFlow, we would define a tensor that is a description of a multi-dimensional array. It may have the shape and the data type, but it does not have the actual value. So in the snippet, we use both TF zeros and NumPy zeros to create a matrix with all elements set to 0, while NumPy will immediately instantiate the amount of memory that is needed for a trillion by trillion matrix, filled with zeros, of course. TensorFlow will only declare the shape and the data type, but not allocate the memory until the part of the graph is executed. Cool, right? So this core distinction between declaration and execution is very important to keep in mind, because this is what allows TensorFlow to distribute the computational loads across different devices, such as GPU, CPUs, GPUs, and TPUs. This is attached to different machines. So with those core building blocks in place, let's convert our simple program into a TensorFlow program. So in general, in this case, it can be divided in two phases. The first phase is going to be construction, and the second one is going to be running. So the construction is for the computational graph, and then running the session that will encapsulate the graph. Here is what our simple program could look like if we wanted to use it in TensorFlow. So let's have a walkthrough to the code. We start off by importing TensorFlow. Next, we create a session object, of course, within a with statement. This has the advantage that the session is automatically closed after the block was executed, and we don't have to call session.close ourselves. Also, these with blocks are very commonly used. Now, inside Hadoop with blocks, we can start constructing new TensorFlow operations, which means nodes, and thereby define the edges اللي هما tensors. For example, This creates a new constant, tensor with the name A, that produces the value 15. The name is optional, but useful when you want to look at the generated graph. We will see that just in a moment when we will generate the graph. But the question now is, where is our graph? I mean, we haven't created a graph yet, but we already add in these operations. That's because TensorFlow provides the default graph for the current thread. That is an implicit argument to all API's functions in the same context. In general, it is enough to rely on the default graph. However, for advanced use cases, we can also create multiple graphs. Okay, now we can create another constant for b and also define our basic arithmetic operations such as multiply, add, and divide. All of these operations are added automatically to the default graph. That is it. That's it. We completed the first step and completely finished the first layout and constructed our computational graph. Now it's time to compute the result. And remember, until now, nothing has been evaluated and no actual numeric values have been assigned to any of those tensors. So what we have to do is to run the session to explicitly tell TensorFlow to execute the graph. Okay, this one is easy. We already created a session object, and all we have to do is call it. We will do session.run, and we give it and pass along an operation. In this case, it's res that we want to evaluate. This will only run as much of the computational graph as needed to compute the value of res. This means that in order to compute res, we have to compute preprod and sum, and as well as a and b. Finally, we can print the result, that is the tensor returned by the function run. So this looks very familiar, does it? By the way, TensorBoard is only great for visualizing learning, but also to look and debug your computational graph. So definitely check it out. Okay, I forget to tell you that after this part, we export the graph and visualize it with TensorBoard. This is how it should look like. So, okay, enough theory. Let's get straight into the code. Okay, we are done with TensorFlow Basic. I'm sure this is the most basic stuff you need to know about TensorFlow before starting it. So I hope it is simple and understandable. And by the way, knowing the basic is not enough. Get your hands dirty with coding. Also, let me know how you found this first part of the talk. Now let's move on to more complex stuff and advanced stuff. And I think I will be taking a 2-minute break to catch up some breath, and then we can finish. Okay, let's get back to our work. So for the next part, we will be implementing TensorFlow's API from scratch. We will try and build something similar to TensorFlow. This way we will understand how it works, and then we can know how to use it. So Our goal here is to mimic the basic operation from TensorFlow in order to mirror our simple program with our own API, just like we did a moment ago with TensorFlow. So earlier, we learned about some of the core building blocks, such as variables, operations, or graphs. These are the building blocks we want to implement from scratch. So let's get started. So the first missing piece is the graph. A graph contains a set of operations, objects, which represents units of computations. In addition, a graph contains a set of placeholder and variable objects, which represents the unit of data flow between local operations. So here we go. For our implementation, we essentially need tree list to score all those objects. Furthermore, our graph needs a method called asDefault, which we can call to create a global variable that is used to store the current graph, ULA instance. This way, we don't have to pass around the reference to the graph when creating operations, ULA placeholders or variables. So the next missing piece are operations. To recall, operations are the nodes in the computational graph and perform computations on tensors. Most operations take 0 to many tensors as input and produce 0 or more tensors object as output. In a nutshell, an operation is characterized as follows. It has a list of input nodes. It implements a forward function. It implements a backward function. It remembers its output and adds itself to the default graph. So each node is only aware of its immediate surrounding, meaning it knows about the local input incoming, the local inputs coming in, and its output that is directly being passed on to the next node. The input node is a list of tensors. So it should be a list of tensors superior or equal to 0 that are going into this operation. So both forward and backward are only placeholder methods, and they must be implemented by every specific operation. In our implementation, forward is called during the forward pass or forward propagation, which computes the output of the operations, whereas backward is called during the backward pass or backward propagation, where we calculate the gradient of the operation. With respect to each input variable, this is not exactly how TensorFlow does it, but I found it easier to reason about if an operation is fully autonomous. So meaning it knows how to compute and output and the local gradients with respect to each of the input variables. Note that in this talk, we will only implement the forward pass and we'll look at the backward pass in another talk, inshallah. This means we can just leave the backward function empty and don't worry about it for now. So we can use this base class to implement all kinds of operations. But it turns out that the operations we are going to implement in are all operations with exactly two parameters, A and B. To make our life a little bit easier and to avoid unnecessary code duplication, let's create a binary operation. And then that just takes care of initializing A and B as an input node. So now we can use the binary operation and implement a few more specific operations such as add, multiply, divide, or matmul. In this case, matmul is for multiplying two matrices. For all operations, we assume that the input are either simple scalar or NumPy arrays. This makes implementing our operations simple because NumPy has already implemented them for us, especially more complex operations such as the dot product between two matrices. The latter allows us to easily evaluate the graph over the batch of samples and compute an output for each observation in the batch. When we look at our simple program and its computational graph, we can notice that not all nodes are operations, especially A and B. Rather, they are inputs to the graph that have to be supplied when we want to compute the output of the graph in a session. So in TensorFlow, there are different ways of providing input values to the graph, such as we talked about this before, um, placeholder variables or constant. We have already briefly talked about this and each one of those and how it's time. And now it's time to actually implement the first one, which is the placeholder. So to implement it, as we can see, the implementation for a placeholder is really simple. It's not being initialized with a value, hence the name, and only appends itself to the default graph. The value of the placeholder is provided using the feed dict, optional argument to session.run, but more on this when we implement the session. I will explain it. Let's move on to constants. Constants are quite the opposite of variables, as they cannot be changed once initialized. Variables, on the other hand, represent changeable parameters in our computational graph. For example, the weights and the bias in neural network. It definitely makes sense to use placeholders for the inputs and labels rather than variables, as they always change per iterations. Also, the distinction is very important as variables are being optimized during the backward pass, while constants and placeholders are not. So we cannot just simply use a variable for feeding in constant. Uh, a placeholder would work, but that also feels a bit misused. So to provide such a feature, normally TensorFlow team, they introduced the constants. Here we are leveraging a feature from Python in order to make our class a little bit more constant-like. I will try and explain it, so bear with me and open your eyes. Now, this is one of the trickiest parts of this talk. Underscores in Python have a specific meaning. Some are really just convention, and others are enforced by the Python interpreter. With the single underscore, most of it is by convention. So if we have a variable called, for example, underscore foo, then this is generally seen as a hint that the name is to be treated as a private by the developer. But this isn't really anything that is enforced by the interpreter. That is, Python doesn't have these strong distinctions between private and public variables. But then there is the double underscore, and it is called, if I remember, a dunder. The dunder is treated differently by the interpreter, and it is more just a convention. It actually applies naming mangling. Looking at our implementations, uh, we can see that we are defining a property underscore underscore value inside the class constructor. Because of the double underscore in this property name, Python will rename the property internally to something like maybe underscore constant underscore underscore value. So each prefixes the property with the class name. This feature is actually meant to prevent naming collisions when working with inheritance. However, we can make use of this behavior in combination with a getter to create something somewhat private properties. What we did is we created a dunder property, which is underscore underscore value, exposed the value through another publicly available property, value, and raised a value error when someone tries to set the value. This way, user of our API cannot simply reassign the value unless they would invest a little bit more work and find out that we are using a dunder internally, so it's not really a true constant, and more like a const in JavaScript. But for our purpose, it is totally okay. This is at least protects the value from being easily reassigned. So there is a okay, let's move on to variables. There is a qualitative difference between inputs to the computational graph and internal parameters that are being tuned and optimized. As an example, take a simple perceptron that computes, for example, y equals w multiplied by x plus b. While x in this case represents the input data, w and b are trainable parameters. That is variable within the computational graph. Without variable training, a neural network wouldn't be uh, possible. In TensorFlow, variables maintain state in the graph across calls to session.run. Unlike placeholder, that must be provided with every call to the function run. Implementing variables is easy when we want to do it. They require an initial value and append themselves to the default graph, and that's it. At this point, I'd say we feel quite confident constructing computational graphs. We have implemented the most important building blocks to mirror TensorFlow's API and rewrite our simple program with our own API. There is just one last missing piece and that we have to build, and that's the session. So we have to start thinking about how to compute the output of an operation. If we recall from the beginning, this is exactly what the session does. It's a runtime in which operations are executed, and the nodes in our graph are evaluated. So from TensorFlow, we know that a session has a run method, and of course, several other methods, but we are only interested in this one particularly. So run takes two parameters as an operation to be executed, and a dictionary feed dict, so that maps graph elements to the value. This dictionary is used to feed in values for the placeholders in our graph. The operation that is provided is a graph element that we want to compute an output for. In order to compute an output for the given operation, we have to topologically sort all nodes in that graph to make sure we execute them in the correct order. This means that we cannot evaluate add before we evaluate a constant a and b. Topological ordering can be defined as an ordering of the nodes in a directed acyclic graph, where for each directed edge from the node, for example, A to the node B, node B appears before A in the ordering. Here is an animated illustration of the algorithm in action for our specific computational graph. So the algorithm is pretty straightforward. Pick any invisited node. In your example, this is the last computational node in the graph, which is passed to session.run. Perform depth first search by recursively iterating over the input nodes of each node. And then if we reach a node that has no more inputs, mark that node as visited and add it to the topological ordering. When we topologically sort our computational graph beginning with div, we end up with an ordering where the constants are evaluated first. Then we operate on mul and add and finally div. Note that topological ordering are not unique. The ordering could also be 5, 15, and add, multiply, and then divide. And it really depends on the order which we process the input nodes. This makes sense, does it? So let's create a tiny utility method to topologically sort a computational graph starting from the given node. Okay, now that we can sort a computational graph and make sure the nodes are in the correct order, we can start working on the actual session class. This means creating the class and implementing the run method. So what we have to do is the following: topologically sort the graph beginning from the operation provided, iterate over all nodes, and differentiate between different types of nodes and compute their output. Following these steps, we end up with an implementation like that could look like something like this. It's important that we differentiate between the different types of nodes because the output of each node may be computed in a different way. Remember that. When executing the session, we only have actual values for variables and constant, but placeholders are still waiting for their values. So when we compute the output for a placeholder, we have to look up the value in the feed dict provided as a parameter. So for variables and constants, we can simply use their value as their output. And for operations, we can collect the output for each input nodes and call forward operation, and we call forward function on the operation. So wow, we did it. At least we have implemented all of the parts needed to mirror our simple TensorFlow program. Let's see if it actually works, shall we? So for now, let's put all the code for our API in a separate model called gf_api.py, and we can now import this model and start using it and using whatever we have implemented. So basically, this is the main file. This is how it should look like. So we have imported our all previous codes in the gf_api as a gf. Now we have our own TensorFlow, and when we run this code, assuming we have done everything right so far, it will correctly print out 3.75 to the console. This is exactly what we wanted to see as an output. This looks intriguingly similar to what we did with TensorFlow, right? The only difference here is that the capitalization. So, but that was on purpose, while in TensorFlow, literally everything is an operation. Even placeholders and variables, we didn't implement them as operations in order to tell them apart, and I have decided to lowercase operations and capitalize the rest. So congratulations, you have successfully implemented some core APIs from TensorFlow. Along the way, we have discovered computational graphs, talked about topological ordering, and managed to mirror a simple TensorFlow program using our own API. By now, I hope that you feel confident enough to start using TensorFlow if you haven't already. So while creating this talk, I was diving deep into the source code of TensorFlow, and I am really impressed by how well written the library is. With that said, I want to emphasize once more that what we have implemented is not 100% how things works in TensorFlow, because there are quite some abstraction, and TensorFlow is way more complete. But I wanted to make things easier and reduce it to the core concepts. This is TensorFlow core. This is how TensorFlow should look like, how TensorFlow could be understood. If you dive deep, you will understand more and more and see more implemented stuff, and you will be impressed by how smart these guys are. So I hope that this talk was helpful for you and that TensorFlow is now a little less intimidating. So you can go find tutorials on tensorflow.org/beta. Maybe you can just use tensorflow.org/tutorials. And another tip you can use is that today I focused on the TensorFlow 1.x tutorials and 1.x version. So if you want a more advanced version, try to avoid gf enable eager execution and gf session.run and gf placeholder and feed decks, because this exists only in the first in the gf 1.x. So basically, we will see if we can find a way to work on advanced stuff later. So some books you can use is two of our favorites as data scientists is Hands-on Machine Learning with Scikit-learn and Keras and TensorFlow 2.0. And you can use also Deep Learning with Python. It's also a good book. So yeah, in this talk, we have implemented the foundation, and in another one, inshallah, we will build on top of this and implement the backward path, including a gradient descent optimizer. Why not? This will be for sure another fun journey. Till then, happy coding. And if you have any remarks, feel free to leave a comment below or reach out to me on Twitter. Try it out yourself and let me know how it goes and share it with me. And I would love to see what we will come up with. So basically, the event has ended. I will translate. We will go to a group in Google Meet. We will do a meeting now, and I will be available live. Then we can have the chance to test this code, and I will be assisting you throughout running the code and testing it and see if it works. Also, if you're interested, we can do a code lab there. I hope everything is good. All right. And one thing, one of the organizers of the team is asking me to tell you that we are open for recruiting people. So if you want to major in TensorFlow, want to learn TensorFlow, I hope you can check our pages, our social media, or our group. There is a link, there is a form, you can fill it, and then you can join us, and we can do events like this, or we can just learn TensorFlow together. Thank you very much.